not only can you find the Gibbs free energy or the available work for a general reaction, so the work per mole that's available, but you can actually find out how much work you could get for a particular amount of substance either consumed or produced in a reaction. So this is the same as what we were just doing, except for we're going to add on one more step where we have a very specific amount of reagent that's either used or a product that is produced during the reaction. So in this example, we want to calculate the maximum work available when 0.72 grams of copper metal is produced in the following cell, where we have iron turning into iron 3 ions and copper 2 ions turning into copper solid. Now remember from chapter 18 that Gibbs free energy, right, delta G is equal to the work max. We're going to use the same equation, and also remember that delta G, now that we're talking about electrochemical cells, is equal to the number of moles times Faraday's constant times the cell potential. So in order to know how much work we could get from this particular cell, we need to know three things. We need to know how many moles of electrons are transferred during it. We need to know, remember what Faraday's constant is, that's probably the easiest one, and we need to calculate the potential of the cell. So let's start with N, finding how many moles of electrons are transferred in this reaction. First we want to write the half reactions. So iron is turning into iron 3 plus. We want to balance that, so we want to balance that by adding 3 electrons. And copper ions are turning into copper metal. We need to balance that by adding 2 electrons. Then, to know how many moles of electrons are transferred, you want the moles transferred in the whole thing. In this instance, we have 3 electrons here and 2 electrons here. You can't transfer 3 electrons and have the copper only accept 2 of those. They have to be the same. So we can make this electron 6 if we multiply these irons by 2 and then multiply the coppers by 3. So now we have 6 moles of electrons being transferred in this reaction. Okay, so then the next main step is to find the cell potential of the cell. For that, you'll need your handy-dandy reference sheet, and you'll need to find the equations that you're looking for. Iron, just like copper, has multiple possible oxidation states, so make sure you're finding the iron that you're interested in. In this case, we have iron 3 going to iron metal. We have iron 3 going to iron 2 plus. Since in our reaction, the iron 3 was going to the metal, this is the one we're interested in. And also, we're interested in the copper, where the copper was going to the metal now. These are both reduction potentials, remember, but one of ours is being oxidized. Which one have we oxidized over here? We've oxidized the iron because it has lost electrons. These electrons are over here, right? So our electrode potential is not the negative 0.4 that we see on the chart, but it's a positive 0.4 volts. And for our copper, the cell potential is 0.34. Sorry, the electrode potential is 0.34 volts. Notice, this is very important and very counterintuitive. Although we have multiplied these reactions over here by coefficients, we did not change the electrode potential. The electrode potentials are intensive property, meaning they're independent of the amount of substance, so don't multiply those by the same coefficients. Alright, so then to find the cell potential, we add these two together, meaning our cell potential in this case is 0.38 volts. Now we just have to put all that information together. So I've brought those values over here. Remember, delta G is equal to negative NFE cell, and it's also equal to work max. So we can say our delta G is equal to negative 6 moles of electrons times Faraday constant, 96,485 coulombs per mole of electron. All right, and then our E cell If you multiply all of that together, you get negative 219,986 Coulomb volts. What the heck is a Coulomb volt? Lucky for us, a Coulomb volt is also equal to a joule. So this is negative 219,986 joules. This is as far as you've seen before. What's new is in this particular question, we had a particular amount of copper that was made. So we had 0.72 grams of copper. So this is the joules that you would get per mole of a reaction. And we want to know how many joules you would actually get for getting 0.72 grams of copper. So if you have 0.72 grams of copper, we can easily convert that to moles. Copper has a molar mass of 63.55 grams and 1 mole. Then you want to look back at your reaction and see how many moles of copper went into your reaction. So back here we see that copper, we put 3 moles into the reaction. So that means that we need to put that same 3 moles of copper here. So we have 3 moles of copper per 1 mole of the reaction. And for every 3 moles of copper, we get this much work. So negative 219,98,006 joules. If we multiply all that out, that means that if you got 0.72 grams of copper, you also got 831 joules of energy. Don't forget to check for sig figs because this here only has 2. That means that we can only say we got 830 joules of energy.